Good afternoon. Welcome to this session. It's my great pleasure to introduce Professor Paul Bonnington, who is the Director of the Monash E-Research Centre, Monash University, Australia, and a Professor in the School of Mathematical Sciences. Oh, that sounds really impressive, and I've got a daughter with dyscalculia, so I'm really impressed. He began his academic career at the University of Auckland, New Zealand in 1993, becoming an Associate Professor in Mathematics, President of the Combinatorial Mathematics Society of Australasia, Chief Managing Editor of the Australasian Journal of Combinatorics, and Associate Dean of the Faculty of Science. In 2005, Professor Bonnington spearheaded New Zealand's e-research infrastructure project, BestGrid, and was recruited by Monash University to lead their e-research centre in 2008. This multidisciplinary centre has grown rapidly over the past 8 years and now includes over 40 e-research professionals, providing expertise, computing, visualisation and data capabilities to numerous research domains covering a really wide field, including archaeology, genomics, structural biology, biomedical imaging, climate modelling, computational chemistry, materials engineering, fluid dynamics, transport and public health research, as well as geophysics and mathematics. The Monash E-Research Centre's role is to build collaborations between research disciplines, nurture e-research developments, and to build bridges between researchers and research infrastructure providers. And we've seen a number of presentations talking about the importance of supporting research in all of our organisations today already. Since 2010, the Monash E-Research Centre has been selected to host over $20 million worth of Australia's federally funded national e-research infrastructure for specialised high-performance computing, research cloud services, data storage and data management. And that's done under the auspices of the National Computational Infrastructure Specialist High Performance Computing Facility. The innovations of that centre, particularly with respect to cloud infrastructure, real-time instrument data processing and virtual laboratories, is internationally regarded, and it partners as a centre of excellence with many of our technology companies. So please join me in welcoming Professor Bonnington.
Okay. Hopefully you can hear me. Good. Now I've got a clicker here. Okay, so thank you very much to the organising committee. It's an absolute privilege and pleasure for me to be presenting here at THETA. You probably can tell from my accent that I am a New Zealander, as Liz pointed out, so I thought I'd just spend a quick moment just talking a little bit about myself. So, as Liz said, I'm a mathematician, combinatorial mathematics and computing. And it's my effort actually recognising that in order to further my research, I needed to actually start to think about the infrastructure that I was using to support combinatorial computing. And I also recognised that I couldn't do it alone. And so I partnered with a physicist, a chemist, geologist, and the list goes on, in order to create a research grant which actually got some infrastructure into the University of Auckland, where I was eventually, for my sins, established as the first Associate Dean of IT in the Faculty of Science. The Dean was actually so impressed that I managed to get people from other departments within his own faculty to work together for the first time that he gave me this role. So I was there at the University of Auckland for 16 years, and then almost a decade ago I moved to Monash University in Melbourne, where I've been heading up the e-research centre, as Liz pointed out. But I'm proud to say, because I'm actually here back in New Zealand, that I am a proud New Zealander, and I am still an All Black supporter. Part of that actually relates to the fact that people in Melbourne really don't know much about rugby, and so I can proudly talk about the All Blacks. I was really pleased to see that last night you had a jazz trio playing at the welcoming reception. This is my first THETA conference, and this is the first time I've been to a conference where there's been a jazz trio. And jazz is actually really important to me. As you can see, I do it in my spare time. I play in groups and jazz clubs in Melbourne, and it actually is a break from computers. It's a very raw activity, and it just gives my mind a rest from the computers. However, the point I'm going to make here is that for you to discover more about our music, you're going to Google the Ish Allen Project and you're going to look us up on iTunes. And in fact, we've just come out of the recording studio and there we generated huge amounts of data in the process of recording because all of that actually is underpinned by advanced computing. And this is my point here with research. Now, here is a researcher, Andreas Flores, at Monash University. He's no longer at Monash. He's moved on to bigger and brighter things with a spin-out company as a result of this work he's been doing here. But here he is doing research. But here he is also using high-performance computers. And in fact, it may look like he's not using a computer, but he is. This is an instrument at the Australian synchrotron. It's a phase contrast X-ray beamline, and it's used for imaging lungs. And in fact, his use of computing in that experiment actually underpinned a world-first discovery. Here you're actually witnessing the first time that breathing lungs have been imaged in 4 dimensions. Now, what you're looking at here is no simulation. This is the real data that came off the detector at the beamline. And this is actually X-ray data. Now, the only thing we've done with the data is we've put a bit of colour in it. People even object to the fact that we've used blue for the lungs, but it just helps us bring out some things that we're interested in. It's a form of segmentation of the data. Now, what this work actually led to was a discovery that disease sometimes can manifest itself in the way that the lungs move before it manifests in other ways, such as a tumour or a blotch on the imaging data set. And so it's actually a tool for early diagnosis of disease before you would actually see this in the more traditional way. But more importantly, his work actually got us to understand better about the mechanics, the biomechanics of breathing lungs. His group was able to see things and appreciate the way that lungs move in a way that no one had ever seen before. And as a consequence of some of this work, they identified that your first breath is actually the most important breath of your life. Now, if that goes wrong, then you may actually develop some lung disease in future in your life. But it also identified that the way that we had been ventilating babies up until now actually possibly was not in their best interests. And that work had led to new ways to ventilate premature babies. So it's a really important mission to be on, the research endeavour. It can save lives, of course. But one thing that Andreas said very early on, he said he wanted capabilities that no one else has. And he wanted capabilities that everyone will need. And so this is a great challenge to have, but it actually describes precisely the journey that we're on. We're actually in the process of co-designing institutional-wide IT environments to support research that nobody else has and that everyone will need. And it's the journey of the unknown. And when we say co-design, what do I mean? I mean actually recognition that all of the components of this actually have an element of the researcher contributing to the IT solution. And also, it's about integration. It's actually about engineering in the gaps. Now, there are instruments, there's experiments, there's the use of desktop tools, there's even web resources and databases and reference data and so on. And all of that needs to come together. And what we do actually is a journey where we're integrating these elements. And that requires engineering, and engineering in those gaps that exist between those elements. Now, can this IT environment that we wish to create for our researchers that lead to new discoveries, can that be left to researchers or their communities to establish? Well, our experience at Monash University is no. Researchers need their institution to help them scale up what they're doing in the lab, on the desktop, with the next instrument. And this is not an environment that is something that you can outsource naturally. And in fact, as I keep coming back to the point, nobody else has this environment today. So therefore, how can you possibly write a contract to an external provider to provide it if we don't even know what it is ourselves? We're actually engaging in a journey of the unknown to build this. And it's important to recognise this is not about viewing this from a service point of view. To build these environments, one doesn't simply just create services and supply those to the research or to the researcher. Because again, we don't know what we're doing. It is the journey of the unknown. And so to go on this journey of the unknown, we do something that works and has worked for hundreds of years in research. That is, you collaborate. And the way we collaborate, I like to call the co-design principle. In fact, when I say co-design, I mean something that's even broader. I actually mean that together with the researcher, we're designing this IT environment or the IT system and platform. We are building it with their participation because they're building components of it themselves. And then together, we cooperate that. And what we've done quite deliberately in Monash University is to start every journey like this with an instrument. And I hope to convince you that instruments are a key to this, to actually get a framework by which one can go on these journeys. So 10 years ago, as Liz mentioned, the Monash established Australia's first university-based e-research centre. Now our mission statement, our goal, our vision, it changes from time to time, but this is what it currently says. It's about enabling and accelerating 21st century discovery. Now, how do we do that? It's not just through IT. It's actually a whole combination of things coming together. It's the application of advanced computing, data informatics, tools and infrastructure. It could be mathematics. And this is delivered at scale. The centre's purpose really is to try and actually get some institutional wins behind this. And it's built with this co-design principle. Now, why does Monash embark on this program? It's simply it's a strategic transformation of the research environment to keep Monash relevant. And it's a transformation that happens at scale. As you can see in some numbers I will present you later on, everything's big. There are 6,000 researchers that engage with our capability to some degree. It's a transformation that looks for the latest in innovation. Now, we have established our relationships with some key providers like Mellanox and Red Hat and so on, who are providing us with technologies before they hit the marketplace for us to work with. It's a transformation that aims to translate research outcomes. Now, it is the case that researchers do participate in this journey to build the environment that will enable them to discover something new. Now, it is the case that sometimes the researcher, once they've got to that point, will move on to the next problem. But the capability is something they wish to maintain, and the institution can work to help translate that environment to be reused and used by other people, and that helps sustains it. And it's also a journey and a program which is about establishing connections with industry partners and connections with other like-minded universities. So there is a strategic intent. Monash does this because we want a world-class research environment, and and that in turn attracts the very best and most talented researchers. There are some things that can happen at Monash that can't happen anywhere, and researchers like that, and they'll come to Monash for it. But of course, this is about improving research performance. Now, of course, it's not written there, but this, of course, in our mind means also it's about rankings. It's about getting the university up in some rankings that then drives student interest, and it can drive and attract the next best students. So I wanted to try and illustrate how our program is actually impacting on research performance, and in particular, what does it do for the most talented researchers? Now, this is a very crude measure of who are the top researchers in the university. I don't name anybody, but the measure we used in this particular study is that we simply took the researchers who generate the most external research dollars and have the most grants awarded to their name. Now, why do we think that that's a crude measure of performance? Well, actually, research grants are often built around track record, and track record comes from performance, research performance. And so here we can see over the last 7 years that the percentage of the top researchers that are utilising, engaging in this co-design journey with us is increasing. It's increasing at a healthy rate. We're up to 60% of the top researchers at the university depend on this e-research program to make their next discoveries. Now, my goal is to get that to 100% by 2020. So what's an example of a top researcher that we would engage with? Here's Trevor Lithgow. He is an Australian Laureate Fellow. This is the tier 1 of researchers within Australia. And he works in an area of structural biology. Now, he will use instruments in order to underpin his discoveries. In fact, he has to generate new data in order to make those new discoveries. And so he would use, for example, an electron microscope that that images cryogenically frozen samples, like the Titan Cryos. He may use optical, and he does use optical imaging techniques, new ones, such as lattice light sheet. And he would work with the neighbouring synchrotron beamline, in particular the crystallography beamline. Now, these generate data, and in human quantities, and I'll show you in a moment how much, that needs to be orchestrated with a processing to get through the fact that this is an inhuman quantity of data. And so a non-human has to process it. So we use a supercomputing facility like the one we have at Monash called Massive to actually do some work with that data in a way that he will describe and in a way that he defines and that his group will code. And from that work, this particular discovery recently that was published in Nature, which of course is where the very best researchers wish to publish, identified, for example, a toxin that causes cholera. Now, there are a lot of groups around the world that are working on cholera and understanding the mechanics of how that disease occurs. Well, he happened to publish first. Now, he wouldn't have been first to publish this result if we hadn't accelerated his discovery process for him with our application of our technologies and the work that we do. Now, unfortunately, there's no prize for being second in research. So acceleration is actually the key to all of this, and it's why we've incorporated that in our mission statement. Now, you may be wondering, so how much data are we talking about? What's the scale of what's going on here? And Trevor Lithgow is one example. So the Titan Cryos is generating, this is the cryo-electron microscope, up to 4 terabytes of data per week. The lattice light sheet is generating up to 1 terabyte of data per week. The synchrotron now has a new detector at the crystallography beamline generating up to 4 terabytes of data per week. And that needs to be processed. There's no point just keeping the data, you have to do something with it. And so the massive supercomputer and the Nectar Cloud at Monash is on an average year generating currently around 63 million CPU core hours. And most of that is dedicated to processing data like this instrument data. So I'll just come back to a point I just made through there. Discoveries of the future will be based on data that hasn't been generated yet. So think about that. Where's that data coming from? Well, it'll come from the next generation of instruments, and it will come from the instruments that already exist. Now, to be fair, I'm not talking about all discoveries of the future will require new data. Of course, there's still a lot of discoveries being made on data that already exists. But what we've done at Monash taken a very deliberate instrument-centric approach to this co-design journey. We start with the microscope, if you like. Now, this is a very old microscope, but it actually serves a useful purpose to describe what I'm going to talk about. We build 21st century microscopes. So what's a microscope? Well, I don't mean the old one like this. I actually mean something that creates an opportunity for researchers to discover something new, to see something for the first time and ask questions and to generate a hypothesis. But if you look at a microscope, it serves as a useful analogy. It has three parts to it. It's got a light source down the bottom, in this case a mirror. It's where the sample goes. It has focusing knobs, and the researcher is turning these knobs and applying new filters. And it's a form of analysis, and it's the focusing that's key. And then there's a lens. There's something that is actually where the researcher is interacting with this environment and seeing things for the first time. And that's where the insight comes from. Well, what's the modern microscope? Well, it's not a single instrument like this. It's actually the seamless orchestration of a number of things coming together to perform those three key roles. It could be, for example, for capturing data, we use a beamline at the synchrotron, or an instrument like a high-throughput genomic sequencer. Or it could even be a series of photographs taken as a part of an archaeological study. What is the analysis environment? Well, it turns out, and you'll see the evidence of this in a moment, that the data coming off that capture layer is growing exponentially. We can't avoid that. It's growing at human speed. So we use a non-human to process it. And that's the supercomputing line. And in fact, the supercomputers are actually focusing the data. They're extracting out the things that we are really interested in looking at further. And then, what is the lens? Well, that's simply the computer screen, because everything's digital. It is where the researcher is interacting with this modern environment. Now, that computer screen could actually be a room-sized multi-display system, such as the CAVE facility at Monash, which is 84 million pixels of display, or it could still be your regular desktop screen. But that desktop screen is providing you a portal into the other layers of the infrastructure. Now, there's something about the microscope which I haven't talked about yet, but is key to how it works. And that is when researchers use it, they're using it interactively. They are constantly focusing, turning the knobs, focusing the data, shifting things around. The sample's not quite aligned, they'll move it somewhere else. It's a total real-time interactive process. And so that's what this modern environment needs to be. We orchestrate all of this with IT, good IT, but the goal here is to integrate, to engineer in the gaps of these layers, and to make this work for the researcher in real time. So Michelle here, up on the right here, is actually working with the instrument down the bottom of this, but doing so from her office. Okay, now here's another key point. This is like a pipeline for the researcher. It's a pipeline for data. It turns out, increasingly, the researchers themselves are coding the elements of that pipeline. Now, here is an extreme version of what I mean to say. This is the acknowledgement section of a paper published in Nature by a group of Monash researchers. And every one of those bold words corresponds to a software package or software module that they wrote or some other person within the international community wrote. And so, as you can see, there's just so many components. It's a very, very complex system that's created. But they make all of these things work together in order to make the discoveries. And so we have to recognise and embrace the fact that these pipelines and these environments are actually getting coded by the researcher along the way. Now, another term I've used, it's integration. And in fact, the type of processing we're talking about now is actually different to what we have had in the past around high-performance computing. I emphasise, for example, that everything's interactive in real time. High-performance computing of the past was not interactive in real time. It ran in a batch mode. You submit jobs and you waited some time and you got back the results. That was well suited to modelling and simulation. But now we're entering a data-centric world, and data-centric processing has to happen in real time. So the use case that I want to come back to in this was the 4D imaging of lungs done by Andreas. It required a whole lot of components to happen and to be orchestrated and synchronized in real time for him to do the 4D imaging. Otherwise, it would only be 3D. He had to rotate the sample and had to ventilate the lungs and synchronize that ventilation by the previous capture of the experimental data, and had to do that a number of times. And he had to process that experimental data as he was capturing it in order to make the synchronization seamless. It required capabilities and tools that were produced by different organisations, and all of that had to come together. Now, there's no service level agreement between these organisations on making this work. It's a very expensive process as well, and a very expensive experiment. So who takes responsibility for making all of this work? Well, I hope to address that in my talk towards the end. I just thought I'd give you one other nice example of that data coming off that beamline in action. So this here is data that came from that beamline. We have done nothing to the data. This is the raw data as it comes off the detector. The one thing we have done is we've coloured it again. That colouring helps from a visual point of view. But as you can see, this is incredible detail, and it's not simulated in any way. In fact, some of you might be astonished to hear that this is actually X-ray data. So it's a pretty amazing X-ray machine. And so here we start to peel away the skin. Now, how do we do that? Well, it's focusing the data. We change the parameters on the software to get it to reveal the voxels, or the pixels, the 3D pixels, of a certain density. And we know bone is of a certain density, so let's just reveal those. And we coloured it again, of course. And there you can see the detail in, by the way, this is a rat, if you haven't already guessed. But you can see the detail in the bones. In fact, again, none of this has been simulated, and it is all real. And researchers are making discoveries like never before. Why is visualization important? And I talked about the lens at the top. It's still really important to get the human into this environment. Now, I like to quote Donald Rumsfeld on this one, please forgive me, but it's a great way of actually just making the point. There are known knowns. These are things that we know we know. There are also the known unknowns. That is to say, we know there are some things that we do not know. But there are also the unknown unknowns, the ones that we do not know that we don't know. Now, computers, if you get a computer to mine the inhuman quantity of data, the computer's only going to find the things you already know about or you already suspect exist. What about the things that you don't know about? That's really what discovery is about. So visualization brings the human back into the big data challenge, and we have plenty of evidence of showing researcher around a good visualization can see things that the computer would never find in a million years, because our brain is still the very best pattern matching machine, and we see patterns where a computer wouldn't see it, and that drives a hypothesis and discovery. Now, a lot of examples that I've been using in this microscope analogy have been from the life sciences. I just wanted to really make clear that I'm not talking just about life sciences. These microscope environments could actually be built for any discipline. And in fact, it could be used to bring together disciplines. So here's some work which was featured on a science program in Australia called ABC Catalyst that we did in support of archaeology. Now, the archaeological sites in question here are in Laos, the Plain of Jars. And unfortunately, there's a lot of unexploded munitions around these sites, so they're not safe places to go physically. However, they are great from an archaeological point of view. So what this group are doing, they're developing the use of drones to fly out over the valley and to, in a semi-autonomous way, to navigate trees and canopies and so on, like a self-driving car, capture the site. And it captures the site by taking a series of photographs, using photogrammetry to reconstruct the 3D environment. Then the researchers come into the lens and they actually, in air-conditioned luxury this time, interrogate the site and make discoveries. And that brings together, of course, a lot of disciplines. Now, there's a growing need for local infrastructure. In a way, I want to point out that high-performance computing, in particular, that middle layer of our microscope, is bucking some of the trends that we're seeing. And how am I going to prove this, or how am I going to give you the evidence of this? And you can't go past this. Now, this graph here is the amount of data that our institutional data storage facility is storing. It's the amount of research data. And it has consistently been growing at 75% per annum. That's a lot. In fact, I can't think of any other growth that's occurring in the university that's at that magnitude. It's a scary graph, and it's a scary thing. Now, that data also needs to be processed. It's not just capturing that data and storing it for use. You've got to actually process it, and increasingly in real time. So that's driving a compute infrastructure on this as well. Now, 75% compounded annual growth rate is scary, but of course, technology will save us, won't it? No. Technology gains that we have witnessed, like Moore's law, for example, or in the case of networking, Butter's law for photonics, these allow us to deal with maybe a 50% at best compounded annual growth rate without something else happening or something else breaking. In particular, what I want to say is that we are generating data faster than we can get it out of the campus. Just by this. It's the growth of that data is actually exceeding the growth of our networks to even get it into maybe a cloud environment. So the research, so we become actually a sink of activity. And the research data compute is increasingly an institutional-wide concern. External technology providers cannot fill the gap. There has to be more involvement at the institutional level. So there's this widening data deluge technology gap. So the university can ask the question, why not just reinvent the problem? Are we really doing the right thing for our research by capturing all this data? Can we just reconceptualize the problem somehow? Well, we have been. We've been reconceptualizing the problem all the way along. And we're still getting 75% compounded annual growth rate. So how do we reinvent this problem? Well, this is a good example of co-design. You need actually the researchers involved in this. They're co-designing the solutions to this new problem. We're reinventing it, and they need to be part, the researcher needs to be part of those solutions. 2008, we instituted good data management practice, where we wanted to make sure that it's the right data being stored for reuse, so it's not lost and it can be reused. 2011, we introduced merit-based allocations. It's the researchers that need to make those judgments on what is meritorious research. 2013, we introduced more tiers in our storage. But it's again the researcher that actually is best positioned to say where the data should be in that tier, that multi-tier storage. 2015, we started throwing data away. Now that'll shock people that we're throwing research data away, but we have to. We have to in this modern age. But we started throwing it away. We started throwing away bad data and working data when it's really not going to be needed again. But it's again the researcher that's best positioned to decide what you throw away. They have to be part of this solution. Now, we've just recently embarked on, with the Faculty of IT, work to actually get more machine learning techniques. Researchers need more tools to deal with this inhuman quantity, so therefore they've started to work on machine learning. But machine learning needs researchers, because you've got to start that process with good research, expertly annotated data, and the researchers need to do that. Now, notice I've got a few more minutes. Yep. Okay, I'll look to wrap up soon. I wanted to say just a few other things about this. I've emphasised the need that things that happen need to continue happening within the institution, and that's scaling up. What about the commercial external service providers? Well, they do have a role, and in fact it's pointed to, and first by CERN, who of course are the hosts of the Large Hadron Collider. They've got the biggest data problems. But they've pushed, and this has been adopted as best practice in the research infrastructure sector, as hybrid cloud HPC model. It's really got three pillars to it. The first pillar, local high performance infrastructure to accelerate discoveries. And that's high performance at the extreme and right across the board, not just compute, but storage and even networking. Second pillar, local infrastructure as a service. We need to actually get researchers the environment to help them to continue to co-design. And they do that through self-service provisioning. And they do that exceptionally well, increasingly. And we're seeing a lot more demand in here than we anticipated. And then the need to occasionally burst out to a commercial cloud provider. And ideally that would be using essentially the same technology stacks you're using elsewhere. And in our case, for us, that's OpenStack. Now, associated with all of this, of course, are the repositories. The repositories are still the place where a lot of reuse and a lot of data ends up. And that needs to continue to drive direction within the research community. One message I have going forward, and if you're wondering how does your institution actually start a journey like we've been through at Monash, it actually starts with what I call the research professional. Most of our e-research staff have research backgrounds. Many have PhDs. They've even considered embarking on an academic career, but they've actually chosen a path where they wish to enable and accelerate somebody else's research. And this is crucial to the co-design principle. Having these research professionals, they are the ones who are acting as the glue. And this is linked to a number of challenges that institutions face when establishing this type of program. Prioritisation. How does the organisation prioritise? And I have to say, it actually begins by supporting excellence within your organisation. And of course, inevitably, that will mean that there are some haves and have-nots. We are driven to be everything to some key research groups, particularly centres of excellence. Also, key going forward, everything has to be software defined. We need the most agile environment within to create these IT environments. Software defined infrastructure is key to this. It has to be agile. And when I say software defined infrastructure, I mean not just the compute and storage, I actually also mean the networking. Now we're about to start to have researchers programming switches on our research network to help integrate their instruments with the rest of the layers of the microscope. And coming back to it again, we need to recognise that third career path, recognising the research professional. Organisational structures. No one group within the organisation can do this program alone. It actually requires partnerships. And of course the big question that many of you might be thinking, who takes responsibility for all of this? Particularly when components of a co-designed system fail. There'll be a lot of finger pointing going on here, wouldn't there? Well, not necessarily. And our experience is that that can be overcome. And it can be overcome by, first of all, recognising this is not about services to the researcher. That view doesn't work. What does work is actually getting the researcher to appreciate you as an equal colleague, an equal partner in this unknown, ambiguous journey. And in fact, I come back to a document which was first published in 2006, which actually has still the most important messages that I've seen in this whole area. It was actually a report to the National Science Foundation in the US around cyber infrastructure program, and it was actually an examination of the previous 10 years that they had in 2006. It's still relevant today. And one section is actually this: leadership should be a partnership between technologists and research domain specialists. If you get that right, then the whole question about who takes responsibility solves itself. It's the researcher that ultimately we would like to take responsibility, and they take a sense of ownership in this, and they actually help sustain what we do. So closing the loop, what can we do as a community like THETA? Do what universities have done for hundreds of years. Let's collaborate. Let's share the technologies, work together on open platforms, foster a culture of knowledge exchange, particularly around technologies, emerging technologies that are important to us like OpenStack, Ceph and Cumulus. More research cloud nodes always helps, and I'm pleased to see that University of Auckland have actually established a research cloud node, which is linked to the Australian Nectar Research Cloud. And that's fantastic to see, because now suddenly I can collaborate with my old institution in a way that I couldn't before. Sharing co-designed code and platforms. Research communities do it very well within their community, but we're talking about things that are a layer above. Let's start to share those codes. Let's establish foundations around code bases, like the one that we're most proud of, which is an instrument integration platform called MyTARDIS. And then I come back to the point yet again, as a higher education sector, and the Vice-Chancellors need to be on board with this one, let's start to recognise that third career path. It doesn't work for us necessarily that we have academics and professionals. There's something in between that we have to recognise, value and promote, and that will promote the development of the staff that will take this co-design principle forward. And so with that, I thank you.